Good morning, Namaskar. Am I audible? Please check audio and video. In the last class, we completed semiconductors. Today, we will begin with the third part of this chapter, that is insulators. So, next topic is insulators. Yeah, dielectrics. These are also known as dielectrics. Suppose you have a metal. So, metals are having large number of free electrons. When you apply voltage, these electrons take energy from the voltage and they start moving, because of which you get a current. That we have discussed in the topic named as conductors. But suppose we have non-conducting material. So, if we have non-conducting material, it means we do not have sufficient free electrons. So, we do not have electrons, free electrons. That's why the material is non-conductor. But we are having electrons in each atom which are bound electrons, basically valence electrons, which have participated in the bond formation. And there is a nucleus. So, we have atom like this, plus here and electrons uniformly distributed here. Positive charge is at the nucleus, and electrons are uniformly distributed in each atom around the nucleus in an spherical volume. Physics कहती है कि if the charge is uniformly distributed on a body, then the effect of charge can be considered at the center of the body. So, here negative charge, which is electrons as per wave mechanical model, they are uniformly distributed in a spherical volume around the nucleus. So, the effect of this negative charge can be considered at the center of the sphere. It means effectively positive and negative charges can be considered at same point. Effectively, actually my electron is moving around the nucleus, but effectively the effect of that negative charge, which is distributed in a spherical volume, can be considered at the center of the nucleus, right? So, this is the case in an atom when we are not disturbing the atom, जब हम atom को disturb नहीं कर रहे हैं. Let us suppose हमने एक voltage लगा दिया. We applied a voltage across this non-conducting material. We applied a voltage across this non-conducting material. So, the positive end of voltage will try to attract electron, and negative end of the voltage will try to attract nucleus. So, because of this attraction force, these electron cloud center will shift somewhere here and nucleus will go somewhere here. So, there would be a distance between positive and negative charges. A distance will be created between positive and negative charges. This is known as dipole, right? So, what I am saying that under the influence of electric field, each atom will get polarized. Each atom will get polarized. हर एक एटम पोलराइज हो जाएगा. हर एक एटम पोलराइज हो जाएगा. Under the influence of applied electric field, each atom will get polarized. This cannot be observed into the metals, because metals are having free electrons. The electrons will start moving. Take this energy from the voltage, they will start moving. But here electrons cannot move. So, as much as their bond will allow, they will shift, basically the whole electron cloud will shift this side of each atom and nucleus will shift. So, certain distance will be created between positive and negative charge centers, and hence each atom will become a dipole. Dipole means, di means two, pole means ends. So, two different ends, one is positive and another is negative end. And this phenomena of creation of dipole is known as polarization. So, these materials which are non-conducting, under the influence of electric field, they will, electric field means voltage, they will become polarized, they will get polarized. This polarization is very useful for us. Why? You see, we make a device that is known as capacitor. The purpose of this capacitor is to store charge. These are two metal plates, and on these metal plates we are wanting to store charge. These are metal plates, and on these plates we are wanting to store charge. Charge means voltage. Let us suppose we are wanting to store charge equal to 100 electron. 100 इलेक्ट्रॉन के बराबर चार्ज हम लोग स्टोर करना चाह रहे हैं इन प्लेट्स पर। We cannot fill conducting material between the plates. If a conductor is filled between the plates, then the flow of current will take place. No charge will get stable on the plates. So to store the charge, there must be a non-conducting material between these two plates. Right? कोई कहेगा कुछ भी भरने की जरूरत नहीं है, एयर रहने दो, वैक्यूम रहने दो. Someone may say that we need not to fill anything. Let us put the air or vacuum, that is sufficient. So assume that. Initially, suppose I am assuming that we are not filling anything between the capacitor plate, there is just a vacuum. कोई बात नहीं. These electrons will start to travel to these plates. One by one, these electrons will be reaching to this plate. Let us suppose at any moment of time, 10 electrons are reaching to this plate. So equivalent to 10 plus positive charge will be available here, right? 10 minus here and 10 plus here. Suppose 11th electron goes here, 11th electron is going here. So already reached 10 electron will repel the 11th electron. This will not be able to reach on the plate, and if this electron is not able to reach on the plate, it will not get stored. What I am wanting to tell you, we wanted to store 100 electrons, but we could store only 10 electrons. It means the capacity of the device is not very good as per our expectation. So we are wanting to enhance its capacity to store. How can capacity to store enhance? If these all charges reaches to this plate, but already reached 10 electrons are repelling it, so it is not able to reach that plate. So to enhance the capacity of this capacitor, we put a non-conducting material between the plates. When we put non-conducting material, in the non-conducting material there are atoms. So these atoms will get polarized like this. They will get polarized like this. Now the polarization is happening, plus is happening here. So this plus will attract electrons from the battery. So stronger the polarization, more will be the electrons attracted towards the battery, and hence capacity to store charge will enhance. So these non-conducting materials can be used to design a very important device that is known as capacitor. They can be filled between the plates of capacitor, and when they get polarized, they can attract more electrons, and hence the capacity to store charge can be increased, right? Higher the polarization, more will be the charge coming to the plate, and if more charge is coming to the plate, higher would be the storage capacity of the device. But here I have written two things. I have written insulator as well as dielectric. So are these both same? Is there any difference? There is a minute difference we need to understand. Both are same materials, but still we need to understand there is a minute difference. Suppose there is a naked wire, copper wire, let us assume that, and some current is flowing through that wire. अगर गलती से किसी का हाथ पड़ गया, he will have wonderful experience of life. He will get an electric shock. To avoid that electric shock, what we do? We put a jacket, plastic की jacket, that is basically PVC और nylon की बनी हुई jacket हम उसके ऊपर पहना देते हैं. Right? This plastic is an insulator. Here we are bothering about the resistance of the plastic. If resistance of plastic is very high, then it will isolate the user and the live conductor. So user will not get shock. So here the purpose of this non-conducting material is to provide electrical isolation between two conductors. One is live conductor wire and another is the user. Here we do not want this material to be polarized. If plastic will get polarized, then top surface will create any charge, and that charge may give shock to us. So we would be wanting to use such a non-conducting material which has very high resistance but not very good polarization. Such materials are known as insulators. But if I am putting any non-conducting material into the capacitor plates, then I want that it should be strongly polarized. So a material will get strongly polarized only then it can be used to make the capacitor. So here we are bothering about the polarization because we have to store the charge. So if the material is used mainly to make a capacitor and we are concerned with the polarization property, then it is known as dielectric. So we can have same material for both purposes, but if we are observing it from insulation purpose, then it is known as insulator, and if we are observing it from capacitance purpose, then it is known as dielectric. So let us first define this insulator and dielectric thing, and then we would be moving forward. So we can write, हम लोग लिख सकते हैं, this is the first slide, कई सारे लोगों ने पूछा है, we have just started from here, right? We can write like this: non-conducting materials do not have sufficient free electrons to take part in normal conductivity, but these materials have abundance of bound charges, because of which they get polarized, on the application of an electric field, on the application of an electric field, The materials which get easily polarized, under the influence of electric field, are known as dielectrics, You can write like this also: if the main function of non-conducting material is to provide electrical insulation, then material is known as insulated. If the main function of non-conducting material is storage of charge, if the main function of non-conducting material is storage of charge, then material is known as dielectric. Then material is known as dielectric. This is all about the definition of dielectric and insulator. डिक्टेट, ऋत्विक ने कहा कि सर कुछ डिक्टेट कर दिया करें। बेटा क्या प्रॉब्लम क्या है ना, मैं डिक्टेट करता हूँ, सो सम ऑफ यू से दैट कि फिर से करो। अब वो फिजिकल क्लास में तो समझ में आता है, वर्चुअल क्लास में समझ में नहीं आता है कि कहाँ से छूटा, कहाँ से दोबारा करना है। तो मैं वो सोचता हूँ कि लिख ही दूँ, बेहतर रहेगा। यस प्रतीक, वंडरफुल एक्सपीरियंस कई बार इतना वंडरफुल हो सकता है कि इट में बी द लास्ट एक्सपीरियंस ऑफ लाइफ। सो इंसुलेटर ने बचा लिया कि वी कैन हैव अदर एक्सपीरियंसेस आल्सो। नाउ वी हैव नॉट टू स्टडी मच about the insulators, because in insulator we are mainly interested in resistance. Reciprocal of conductivity is known as resistivity, but we are wanting to explore this dielectric nature of non-conducting materials. So we would be trying to explore things from the dielectric point of view. So dielectrics are basically materials to filled between the plates of capacitor to increase its charge storage capability. This is the first slide. और ना ये टाइम से आया करो। आई एम लास्ट टाइम टेलिंग यू, इफ यू आर लेट then don't say to so this slide that slide and rhythm break होता है, ठीक है। सिलेबस भी कंप्लीट करना है, कई दिन हो गया पढ़ते हुए, मुझे लगता है 7-8 लेक्चर हो गए हैं, तो कंप्लीट भी करना है। सो आई विल एडवाइज दैट कि प्लीज़ इफ़ यू गेट लेट देन वीडियो जब अपलोड हुआ करे तो जो भी 10-15 मिनट आपका छूटा रहा करे वहाँ से देख लिया करें। डोंट ब्रेक दिस रिदम कि पीछे दिखाओ, आगे दिखाओ, ऑल दैट थिंग्स, दैट्स आर नॉट गुड, right? So we are wanting to explore this material which is used to make capacitor. Basically it is filled between the plates of capacitor to enhance its ability to store the charge. So let us see what is ability to store charge, means what is capacitance, and how this material is going to enhance that capability. So put a heading capacitance. Capacitance. Let us consider a parallel plate capacitor. Let us consider a parallel plate capacitor. Let us consider a parallel plate capacitor. This is our capacitor. I am assuming initially that vacuum is filled between the plates of the capacitor. Let us assume initially there is vacuum, because we are wanting to see how much capacity is enhanced. So we have to take the reference. So initially we are assuming that the reference is vacuum. So let us assume that vacuum is filled between the plates of capacitor, between the plates of capacitor, between the plates of capacitor, vacuum भरा गया है। So capacitance is equal to epsilon naught A by D. This is the value of capacitance. A is area of the plates. Area of the plates. D is distance between the plates. Distance between the plates. And epsilon naught is permittivity of free space or vacuum. free space or vacuum. So this epsilon naught is 8.854 into 10 to the power minus 12 farad per meter. रटना नहीं है, just बता रहा हूँ. No need to memorize this value. This is the capacity to store charge. Higher the value of capacitance, I am representing it by C naught. C naught is capacitance. When vacuum is filled between the plates, capacitance. Capacitance is ability to store charge. Now, let us assume that a dielectric material is filled between the plates. Now, let us assume that a dielectric material is filled between the plates of capacitor, between the plates of capacitor. Now let us assume that dielectric is filled between the plates of capacitor. So let us suppose a dielectric material. This is the dielectric material. This is dielectric. Now capacitance can be given as, let us assume that a dielectric material is filled within the plates of capacitor. So capacitance C is equal to epsilon R epsilon naught A by D, that is epsilon A by D. This is capacitance. Epsilon is permittivity of free space. Permittivity of material, basically dielectric material. Permittivity of dielectric material. This is permittivity of dielectric material. Epsilon is equal to epsilon R into epsilon naught. Here you see, my dear friend, we are interested in epsilon R because this is the time, the amount by which the capacity to store charge is increasing. So epsilon R is C by C naught, या epsilon by epsilon naught. This epsilon R is telling us relative ability of capacitor to store charge with respect to vacuum. So higher the value of epsilon R, more will be the storage of charge, means better is the dielectric material. So epsilon R is known as relative dielectric constant. Epsilon R is relative permittivity of material, permittivity और डाइलेक्ट्रिक कांस्टेंट ऑफ मटेरियल, इसे डाइलेक्ट्रिक कांस्टेंट भी कहते हैं, डाइलेक्ट्रिक कांस्टेंट ऑफ मटेरियल. इट इज नोन एज रिलेटिव परमिटिविटी और डाइलेक्ट्रिक कांस्टेंट ऑफ मटेरियल. यू सी फॉर वैक्यूम इट्स वैल्यू इज 1 बिकॉज वैक्यूम के लिए सी की वैल्यू क्या हो जाएगी, सी नॉट बाय सी नॉट इज कैंसिल, सो इट इज 1. अपार्ट फ्रॉम वैक्यूम फॉर एनी अदर मटेरियल इट कैन नॉट बी इक्वल टू 1. Because we are making vacuum as a reference, and with respect to that we are wanting to see whether capacity to store charge is higher or not. So epsilon R is 1 for vacuum. It is 1 for vacuum. For air we use 1, but it is actually 1.0006 for air. So it is slightly greater than 1. Epsilon R is 1.000684 for helium at standard temperature and pressure. Sometimes you use 1 for helium also, but it is slightly greater than 1. That I want to tell you. Then epsilon R is 81 for distilled water. Normal water is very good conductor of electricity, but distilled water is insulated. Distilled water means pure water. Actually, in normal water there are several minerals. So these minerals are available in the form of their ions, and when you apply voltage, these ions move and electrical conduction takes place. But in an distilled water there is no mineral. It is pure water, and if it is pure water, then H2O is a covalent compound, and in that there is no free electron. So if there is no free electron, it is a insulator. It has very good dielectric constant, epsilon r is equal to 81, and that is the reason why आपके घरों में जो इन्वर्टर है उसमें जो बैटरीज हैं, those batteries are nothing but the capacitors, and you put this distilled water between the plates of capacitor to increase its ability to store charge. Some idiots sometimes used to put normal water. No, if you are putting normal water, it means you are putting conductor between the plates, and then the capacity of the battery will decrease, the current will start to flow and heat will get generated, so your battery cannot be able to store sufficient charge, your purpose would be defeated. So never fill normal water between the plates, always try to fill distilled water between the plates. So it is distilled water. Now next, there is a very good compound, that is titanium dioxide. For titanium dioxide, this value is 100. Titanium dioxide is industrially known as rutile. So for rutile, its value is 100, and rutile based compounds are very much used for making capacitor. We store charge on plates of capacitor. So we define a quantity D. It is a vector quantity. It is electric flux density. Electric flux density. Electric flux density is nothing but charge per unit area. Charge per unit area. इसकी यूनिट होगी कूलाम पर मीटर स्क्वायर. इट्स यूनिट इज कूलाम पर मीटर स्क्वायर. Per meter square. Another quantity we know that electric field intensity, right? That I have already defined. It is voltage per unit length. So it is electric field intensity. Electric field intensity. Now, dear friends, D is equal to epsilon r epsilon naught into E. This is our D. ये D की वैल्यू है. दिस इज द वैल्यू ऑफ D. ये D की वैल्यू है. एप्सिलॉन r एप्सिलॉन नॉट इनटू E. दिस इज द वैल्यू फॉर D. ये गॉसेस लॉ होता है एक फिजिक्स में, वहां से निकल करके आया है. दिस इज एक्चुअली द रिफ्लेक्शन ऑफ गॉसेस लॉ. इलेक्ट्रिक फ्लक्स डेंसिटी कैन बी गिवन एज परमिटिविटी ऑफ द मटेरियल. दिस इज टोटल इलेक्ट्रिक फ्लक्स डेंसिटी, दैट इज चार्ज पर यूनिट एरिया stored on the plates in terms of applied electric field. So this was all about the first thing, that is capacitance. Here I tried to define what is the dielectric constant of material. Please note it down. ऋत्विक, दिस वाज द फर्स्ट स्लाइड जब आपने लिखा था. ठीक, इट वाज फर्स्ट स्लाइड, सो कुछ छूटा नहीं है आपका. Today we started from here. This is the first trading. आपको घर पे बैठे रहना होता है, स्टिल यू आर नॉट ऑन टाइम. मैं अपने घर से चल करके स्टूडियो तक आ जाता हूं. But a standard temperature and pressure is nothing but the room temperature and atmospheric pressure को standard temperature and pressure कहते हैं. NTP क्या है मुझे नहीं पता बेटा, हमारे यहाँ ज़रूरत नहीं पड़ती. Abhishek Singh is saying, sir, do the persons from EC and EE memorize all these formulas? Yes, they have to. If you belong from EC and electrical background, then you have to remember each and everything. If you belong from other branches, then you need to understand the theoretical aspect. But if you belong from EC and electrical, then you have to memorize all these. Because EC and electrical में तो numerical problem भी आएगी. You will be getting numerical questions as well. Noted? Right. Next, electric dipole moment. Electric dipole moment. Let us first of all try to understand what is electric dipole. Two equal and opposite charges separated by certain distance. Let us suppose this is plus q and this is minus q. Distance between these two charges is suppose d. It is known as electric dipole. So, two equal and opposite charges separated by certain distance, separated by certain distance constitute an electric dipole, constitute an electric dipole. Two equal and opposite charges separated by certain distance constitute an electric dipole. Yes, GS part is same for all branches. It is GS. I am teaching GS. पता नहीं क्या फर्जी क्वेश्चन पूछ रहे हो तुम लोग, पढ़ाने दो. अरे दिस इज GS, बट इन GS GS इज नथिंग. GS क्या होता है? हर सब्जेक्ट का कॉमन सिलेबस, दैट इज GS. ठीक है, किसी भी चीज़ को जो भी पढ़ा, कहीं भी दुनिया में जो चीज़ें हैं उनको पढ़ा दो, वो GS है. ठीक है, तो GS कोई नई चीज़ नहीं होती है. GS इज बेसिकली दोज व्हाट एवर थिंग्स वी स्टडी इन वेरियस डिसिप्लिन्स, उनका सरफेस पर जो नॉलेज है दैट इज GS. उसी को इन डेप्थ पढ़ लो तो पर्टिकुलर ब्रांच का टॉपिक हो जाता है. भगवान कैसे तुम लोग ऑफिसर बनोगे. Two equal and opposite charges separated by a certain distance constitute an electric dipole. Now we define a quantity that is known as electric dipole moment. What is the electric dipole moment? Basically it will measure how much is the polarization of the material. So polarization means separation of positive and negative charge. So how much charge is being separated and what is the distance of separation? This will tell us about the polarization. So this quantity electric dipole moment, electric dipole moment is defined as magnitude of any one charge, that is q, and distance between the charges. It is a vector quantity and vector direction is from negative charge to positive charge. It is from negative charge to positive charge. This is the vector direction. This is electric dipole moment is defined as. Unit इसकी देखिए, you see the unit of this quantity. Charge की unit coulomb and distance की unit meter. So it is the first unit. There is one more unit. Coulomb meter is written like this. There is one more unit that is known as debye. In the honor of a great scientist Debye. Debye is equal to 1 debye is equal to 3.33 into 10 raised power minus 30 coulomb into meter. This is the conversion between two standard units. Now this electric dipole moment is nothing but magnitude of charge on a dipole and distance of separation between these two charges. It is a vector quantity and vector direction is from negative charge to positive charge. It is a vector quantity and vector direction is from negative charge to positive charge, from negative charge to positive charge. Please put down it. निष्ठा बेटा, पागल हो गई हो तुमको इलेक्ट्रिक फ्लक्स नहीं पता है और तुम इलेक्ट्रॉनिक्स की स्टूडेंट हो और तुम उसको डोपिंग डाउ पता नहीं किस चीज़ से रिलेट कर रही हो। जागो बेटा, पहले जाओ अपना मुंह धुल करके आओ, थोड़ा सा चाय वाय पी करके तब क्लास करना स्टार्ट करो। इलेक्ट्रिक फ्लक्स नहीं पता, यू आर स्टूडेंट ऑफ ईसी, पूरी ईएमटी पढ़ डाला होगा। अरे सॉरी होने की कोई बात नहीं, मतलब थोड़ा अवेयर रहो क्लास में। This is the polarization of a single dipole, but we cannot apply voltage on a single dipole. We would be applying voltage on a material, on a particular volume. So in a volume there would be large number of dipoles. So we need to talk about in terms of a material, not a particular atom. So for that purpose we define a quantity that is known as electric dipole moment per unit volume. This quantity, electric dipole moment per unit volume, is known as polarization. So next quantity is polarization. It is represented as capital P. It is defined as electric dipole moment per unit volume. It is defined as electric dipole moment per unit volume. Electric dipole moment per unit volume. If n is number of dipoles number of dipoles per meter cube means per unit volume, या नंबर ऑफ डायपोल्स पर यूनिट वॉल्यूम लिख लीजिए. वॉल्यूम सेंटीमीटर क्यूब में तो सेंटीमीटर क्यूब, मीटर क्यूब तो मीटर क्यूब. नंबर ऑफ डायपोल्स पर यूनिट वॉल्यूम. And small p is electric dipole moment, electric dipole moment of each dipole. Then capital P is, it is electric dipole moment per unit volume. So in unit volume there are n dipoles, each are having p dipole moment. So p plus p plus p up to n times. It means what? It is n into small p. This is the average electric dipole moment per unit volume. Let us have look for the unit of this quantity. Number per unit volume, that is 1 by meter cube. Number की तो कोई unit होती नहीं. So n is having unit 1 by meter cube, and p is coulomb into meter. So it is basically coulomb per meter square. The unit for polarization is coulomb per meter square. Coulomb per meter is nothing but electric flux D. It means this polarization is nothing but the electric flux density developed inside the material. So now I can say that if there is a dielectric material, this is a dielectric material, and if I apply electric field, so this material will have two kind of charges. One, these atoms which are getting polarized, minus plus, minus plus, minus plus, minus plus, minus plus, minus plus, right? So this value is given as capital P, and some electrons are going from here. So these electrons which are going from here, they will give us epsilon naught into E. So this is due to electric field and this is due to polarization. So overall electric flux density is because of two factors. One factor is applied electric field and the other factor is polarization in the material. So total electric flux density, total electric flux density in a dielectric material, is due to first one, applied electric field. Applied electric field की वजह से जो वैल्यू आएगी एप्सिलॉन नॉट इनटू ई. सेकेंड वन, पोलराइजेशन की वजह से जो वैल्यू आएगी दैट इज कैपिटल पी. सो जो टोटल वैल्यू होगी इलेक्ट्रिक फ्लक्स डेंसिटी की, दैट इज कैपिटल डी इज इक्वल टू एप्सिलॉन नॉट ई प्लस कैपिटल पी. It is equation number 1. This is equation number 1. This is equation number 1. Now we can have D value from Gauss's law. मैंने आपको क्या लिखा है? Epsilon R epsilon naught into E. This is from physics. From equations 1 and 2, they are representing the same quantity. When you know the epsilon r, you can calculate the total electric flux density, or you can calculate total in terms of polarization plus external supplied charge. So this way we are having from equations 1 and 2. They are giving the same relationship, equations 1 and 2. This is epsilon naught E plus capital P is equal to epsilon r epsilon naught into E. So from this, capital P is equal to epsilon naught epsilon r minus 1 into E. This is relationship between polarization and electric field. They may be asking the question how does the capacitance is related with polarization. You see, capacitance is directly proportional to epsilon r, and epsilon r is directly proportional to polarization. So higher the polarization, higher will be the value of epsilon r. Higher the value of epsilon r, more will be the stored charge. It means capacitance. Now you see, this epsilon r is a material property, so epsilon r minus 1 will also be a material property. So from this we can have capital P is equal to epsilon naught chi e into E, where this new symbol chi e is nothing but epsilon r minus 1. It is known as electric susceptibility of material. Electric susceptibility of material. It tells us the ability of material to get polarized. Electric susceptibility of material. It tells us the ability of material to get polarized. This is all about the polarization and electric susceptibility or polarization and dielectric constant relationship. Please note down. Good, Prateek. Done? Shall we go ahead? Now let us talk about types of polarization. Types of polarization. First one is electronic polarization. Electronic polarization. Such kind of polarization is found in all the non-conducting materials. Have a look how. Let us suppose this is an atom and this is a nucleus. Electrons are uniformly distributed in a spherical volume around the nucleus. Let us suppose electric field is 0. Then positive charge is at the nucleus and negative charge is uniformly distributed. So, effect of this uniform distribution can be considered at the center, means at the nucleus. So, no dipole initially in the absence of electric field. So, polarization is equal to 0. But suppose we apply an electric field. So, because of electric field, positive and negative charges will be separated by certain distance. Let us suppose negative charge centers can come this point and nucleus at this. So, there comes a distance between positive and negative charges. So, this distance of separation between these two charges will constitute an electric dipole. So, P does not equal to 0, right. This polarization is coming in picture due to applied electric field. If electric field is non-zero, polarization is non-zero. If electric field is 0, polarization is 0. Such kind of polarization which is coming into the picture due to application of an electric field, it is known as electronic polarization. ऐसा पोलराइजेशन जो इलेक्ट्रिक फील्ड के कारण पिक्चर में आ रहा है उसे हम लोग इलेक्ट्रॉनिक पोलराइजेशन कहेंगे. इट विल बी फाउंड इन ऑल द एटम्स बिकॉज इट इज ड्यू टू द सेपरेशन ऑफ न्यूक्लियस एंड इलेक्ट्रॉन क्लाउड सेंटर. They are leading to the creation of this polarization. So, it is found in all the material types so which are non-conducting. In them this kind of polarization can be observed. So, please you need to write one line. Dictate kar do. Let's dictating this line. Electronic polarization may be induced. लिख लें. Electronic polarization may be induced electronic polarization may be induced in all atoms, in all atoms, in all atoms, in all atoms. It results from a displacement of from the displacement of center of electron cloud, center of electron cloud, center of electron cloud, center of electron cloud, center of electron cloud to the nucleus of an atom, to the nucleus of an atom by an electric field, by an electric field. Full stop. This polarization is found in, this polarization is found in, this polarization is found in all dielectric materials, all dielectric materials. This polarization is found in all dielectric materials and exist only when an electric field is applied, and exist only when an electric field is applied. And exist only when an electric field is applied. Next, second one, ionic polarization. As the name is suggesting, it is found in ionic materials. So, ionic polarization. Let us suppose we have an ionic compound NaCl. So, in NaCl, plus Q and minus Q, they are separated by certain distance, that is their bond length. Let us suppose D. Even if we do not apply electric field, still we have P is equal to Q into D. But if you see in overall volume, polarization is 0. Why? I have told you if it is Na plus, so here Cl minus, here Cl minus, if you recall the crystal structure, here Cl minus, here. So all these dipoles will oppose each other, they will oppose each other, and hence net polarization is equal to 0 if electric field is equal to 0. Although individual dipole is having certain value of polarization, but all these dipoles, since ionic bond is what? A non-directional bond. So non-directional means bond is of equal strength in all the directions. So all these dipoles will cancel each other, and this way you will get non-zero polarization. But suppose you apply an electric field. If you apply an electric field, E does not equal to 0, then what will happen? The bond is stretched. So if the bond is stretched, this is Q and this is like this, it is plus Q and it is minus Q, right? So here you will be having D plus X, it is D plus X. Why bond is stretched? Bond because of electric field. Let us suppose in this direction we apply electric field. So electric field will attract to positive ion one side and negative ion other side. So any one direction bond is stretched. In that direction you see, you will get now X is the length of stretching कि कितना bond stretch हुआ. So P is equal to Q D plus X. So P is equal to Q D plus QX. You see, this QD is 0, this QD is 0, because this will cancel in all the direction, it will become 0, but this cannot be 0. This is due to the electric field induced because of electric field and stretching up the bond. So in ionic material, due to stretching up bond, some non-zero polarization is induced, and that induced polarization is known as ionic polarization, will be observed only in ionic materials. So in ionic material, a polarization is induced, due to stretching of bond under the influence of electric field, Such induced polarization is known as ionic polarization. Such induced polarization is known as ionic polarization. It's known as ionic polarization. Third one. Third one is orientational polarization. Third is orientational polarization. This is due to geometry of molecule. You see, let us suppose we have a molecule C double bond O double bond O. You see here oxygen is negative and carbon is positive. So you have a dipole like this and you have a dipole like this. If you calculate the permanent dipole moment, these will cancel each other. So net dipole moment is equal to 0. This is the net dipole moment, right? Let us suppose you have another molecule H2O. This is H2O. So here you have del minus minus, here del plus, here del plus. Oxygen to hydrogen एक dipole, ऑक्सीजन टू हाइड्रोजन दूसरा डाइपोल. ठीक. नाउ यू सी माय डियर फ्रेंड, यू हैव दिस काइंड ऑफ राइट लॉ ऑफ पैरेललोग्राम लगाइए एंड यू विल गेट द नेट डाइपोल मोमेंट इन दिस डायरेक्शन P net. So this net dipole moment P net does not equal to 0. This non-zero dipole moment is due to orientation of molecule. Here orientation was such that dipoles were 180 degree, they cancel each other. Here orientation is such that this molecule is having certain non-zero dipole moment. This non-zero dipole moments effectively negative charge here and positive charge here. Suppose you apply an electric field, and if an electric field applies force on the positive charge in this direction, then on the negative charge this force will be in this direction. So this force will make a torque and this torque will try to rotate. So electric field applies torque. Electric field applies torque on the dipole and hence dipole align along the direction of field, align along the direction of field, direction of field. When dipoles become parallel to the field, you will get very strong value of polarization, and such polarization is known as orientational polarization. And this is the reason why liquid dielectrics are preferred, because in liquid materials rotation of molecule is possible. Here the alignment of O2 is possible. When electric field is applied, then O2 molecules will align themselves along the direction of field and they would be giving you very high value of polarization. So that is the reason you will be watching that these most of the batteries we are using, they use liquid dielectrics so that rotation of molecule can be possible and this orientational polarization can come into the picture. In solid dielectrics, it cannot come into the picture, because in solids rotation of molecule is not possible, and if rotation of molecules is not possible, then this dipole cannot orient themselves along the direction of field, and hence it cannot contribute into the total polarization. So please draw all this and write down 1 or 2 lines regarding this. लिखें orientational polarization is found in molecules orientational polarization is found in materials that possess permanent dipole moments that possess permanent dipole moments. Permanent dipole moments. Full stop. Polarization results from rotation of permanent moments in the direction of applied electric field. Rotation of permanent moments in the direction of applied electric field. In the direction of applied electric field. Full stop. Now, next point. Next is dielectric strength. Dielectric strength. Basically, strength is ability to withstand certain kind of load. Here the load या external force is our electric field. So any material which can withstand electric field, basically any dielectric material, how much maximum electric field it can withstand without breakdown, that is known as its dielectric strength. किसी डायलेक्ट्रिक मटेरियल पर हम मैक्सिमम कितनी फील्ड लगा सकते हैं ताकि इसका ब्रेकडाउन ना हो, या दूसरे शब्दों में मिनिमम फील्ड रिक्वायर्ड टू कॉज द ब्रेकडाउन, दैट इज नोन एज डायलेक्ट्रिक स्ट्रेंथ. एबिलिटी टू विदस्टैंड इलेक्ट्रिक फील्ड. एक लाइन में अगर लिखें, सो डायलेक्ट्रिक स्ट्रेंथ इज बेसिकली एबिलिटी, या ऐसे डिफाइन कर लेते हैं, it is defined as voltage per unit thickness of material to cause breakdown in it, It is defined as voltage per unit thickness of material to cause breakdown in it. Or in other words, it is the maximum electric field. It is defined as maximum electric field which a material which a dielectric material can withstand without breakdown, can withstand without breakdown. We will always want that we should have high value of electric field. हम हमेशा चाहेंगे कि we should have high dielectric constant, dielectric strength, so that we can apply wider range of voltage across the material. It can withstand wider range of voltage. It is defined as voltage per unit thickness of material. Dielectric strength. One more small definition is required. Spontaneous polarization. Suppose you apply electric field and you get polarization. Now you remove the electric field and still some polarization is found in the material. Then that non-zero polarization is known as spontaneous polarization. What I am saying, you applied electric field on the material, you got certain polarization, you removed the field, still material is containing certain residual polarization. Residual, it's because the input has been removed, still there is some polarization, then this kind of residual polarization is known as spontaneous polarization. Means non-zero polarization in the material in the absence of electric field is known as spontaneous polarization. So you can write certain dielectric material exhibit non-zero polarization even in the absence of applied electric field, even in the absence of applied electric field, this residual polarization is known as spontaneous polarization. This residual polarization is known as spontaneous polarization. This residual polarization is known as spontaneous polarization. Certain dielectric material exhibit non-zero polarization even in the absence of applied electric field. This residual polarization is known as spontaneous polarization. Material will not start behaving like conductor Ankush. Ankush is saying that if we exhibit, we apply electric field more than the dielectric strength, then material will behave like conductor. No, you are idiot. How can it behave like conductor? All the bonds should be broken. When large number of bonds should be broken, then large amount of current flow and that will burn out the material. So breakdown of the device means burning of the device. Device will burn out, जल जाएगा आपका material. आपने देखा होगा बहुत बार धूम ऐसे होली दीपावली हो जाती है, मना लेता है डिवाइस. वो इसी वजह से होता है कि if it gets more voltage then it gets burnt out. How breakdown occur with electric field? What is your question, अखिलेश गुप्ता जी? अरे breakdown होता है. Breakdown में क्या होता है? Failure of the material. So electric field is also a force and every material will have a certain amount of ability to withstand force. So when you give the force more than that ability, material will not be able to be withstand, उसका failure हो जाएगा. That failure of the material is known as breakdown. आइए piezoelectric material, piezoelectric material, very good materials. These are the ionic materials, and in these ionic materials, nature has been very benevolent on us. It has given certain very beautiful materials, and it is one of those beautiful materials. So in these ionic materials, if you apply a mechanical pressure यूनिएक्सियल, किसी एक ही एक्सिस से अप्लाई करें, then positive and negative ions are getting displaced across the thickness of the material. So across the thickness of material, a voltage is induced in the material. This induced voltage is given as Pgt. V is voltage developed across the material, voltage developed across the material, voltage developed across the material. P is applied mechanical stress, या pressure, applied mechanical stress or pressure. G is voltage sensitivity, it is voltage sensitivity, and T is thickness of material, it is thickness of material, it is thickness of material. मजाक मजाक में बहुत बड़ी चीज हो गई. We are giving mechanical force and we are getting electrical output. So this material can be used to convert mechanical energy into electrical energy. It can perform vice versa also. If you give a voltage across it, means electric field, then what will happen? Voltage का positive terminal will try to attract negative ions and negative terminal will try to attract positive ions. Hence negative and positive ions will go away. It means bond will stretch and a strain would be induced in the material. So in these materials you can get change in dimension, that is strain, due to applied electric field. If you vary the electric field such that expansion contraction may take place, then you may get vibration from these materials. So these materials can give you, under the influence of an electric field, mechanical vibration, or under the influence of mechanical force, electrical voltage. So they have both direct and inverse effect. Direct effect, you are applying a mechanical force, you are getting voltage, that is direct effect. You are giving voltage and you are getting mechanical vibration, that is inverse effect. So these materials exhibit both kind of effect. We use them in both ways. Let us suppose this is the microphone through which my voice is getting amplified to you. So in this microphone there is a crystal, piezoelectric crystal. So when I speak, some sound waves are coming and these sound waves put pressure on the piezoelectric crystal. Because of that pressure, some voltage is being developed and that voltage is leading to the current into the wire, and that current is getting amplified. So here the mechanical energy of sound wave is getting converted into the equivalent electric signal with the help of quartz. That is a piezoelectric material. Similarly, you may have seen quartz watches. In those watches we have a piezoelectric crystal and we give electric field from a battery to this crystal. So we give some 5 volt battery, and with that not only 5 volt, you can give any volt required as per your requirement. So you give certain battery and that battery creates an electric field, and that electric field is developed across the crystal. So crystal starts vibrating, and that vibration is connected with the needle, and when crystal vibrates, a needle gets moved because of the vibrational energy. This way the electric energy of battery is being converted into the mechanical motion of the needle of a watch. So that way we are using this material to convert from electrical energy to mechanical energy, or vice versa, mechanical energy to electrical energy. So it has very strong utility in various applications. Please note down few points. Yes, Abhishek, Tesla was very intelligent man, and he has done it, and in future you will also be doing it. Don't worry. In your lifespan it will happen कि we would be transferring electricity without wire. But अभी थोड़ा ज़्यादा दिन लगेगा, but it will happen. Yes, strain gauge में हम लोग इनको यूज करते हैं. You are correct. Please note down. गुरदीप बांबल जी कह रहे हैं कि सर जिनको ब्रेकडाउन समझ में नहीं आ रहा उनको कहिए कि एक बार अपने घर में 220 वोल्ट की जगह 1100 वोल्ट की इलेक्ट्रिक सप्लाई करके देखें. अरे काहे बेटा एक घर ख़त्म करवाना चाहते हो? अरे ये ना लोग एक्चुअली मोस्टली व्हाट हैपेंस विद द स्टूडेंट्स कि उनको लगता है साइंस है तो कुछ बहुत बड़ी चीज़ है. ऑब्जर्वेशन क्लियर रखो. आपने न जाने कितनी बार इलेक्ट्रिकल इक्विपमेंट को फूंकते देखा होगा, जलते देखा होगा. वो जलना उसका नथिंग इज ब्रेकडाउन. सबके घरों में हुआ होगा एक आध बार तो. लिखें प्लीज नोट डाउन. In certain dielectric material, in certain dielectric material, in certain dielectric material, when a mechanical stress, when a mechanical stress या uniaxial mechanical stress लिख लो. when a uniaxial mechanical stress is applied in certain dielectrics, when a uniaxial mechanical stress is applied, then materials get polarized. Then materials get polarized. In certain dielectrics, when a uniaxial mechanical stress is applied, the materials get polarized. The materials get polarized. This phenomena is known as piezoelectricity. This phenomena is known as piezoelectricity. And this phenomena is known as piezoelectricity, and the material is known as piezoelectric material. and the material is known as piezoelectric material. Piezoelectric material. Full stop. In these materials, when an electric field is applied, they get strained. And produced strain is proportional to applied electric field. Proportional to applied electric field. Produced strain is proportional to applied electric field. ठीक है जी. Now, let us try to write few examples. Some popular piezoelectric materials. Quartz, very popular piezoelectric material. Then barium titanate, lead titanate, etc. These are some example. मैंने यहाँ ये बताया कि piezoelectric material में you get both voltage due to pressure and strain due to electric field. So both effects are there. Piezoelectric material में. But there are certain materials in which if you apply electric field, you get strain, and produced strain is proportional to square of applied electric field. In materials में you will not get the inverse effect, means you cannot get a charge due to the mechanical force. But if you applied electric field, you will get strain. So this property of material is known as electrorestriction. This property of material is known as electrorestriction. Please note down, definition is required, nothing more. Just a definition is required. लिखें इलेक्ट्रोस्ट्रक्शन में certain dielectric materials certain dielectric materials get strained when an electric field is applied. Certain dielectric materials get strained when an electric field is applied, but inverse effect is not observed. But certain dielectric materials get strained on the application of electric field, but inverse effect is not observed. But inverse effect is not observed. This property of material, is known as electrostriction. And produced strain is proportional to applied electric field. Produced strain is proportional to applied electric field. Square of applied electric field, sorry, produced strain is proportional to square of applied electric field. Right. आइए नेक्स्ट, फेरोइलेक्ट्रिक मटीरियल. Ferroelectric material. My dear friend, I will not explain anything here because I would be teaching you ferromagnetic material in depth. The only difference between ferroelectric and ferromagnetic is here we are talking about electrical property under the influence of electric field, and there we would be talking about magnetic property under the influence of magnetic field, but the explanation will remain same. So here I am not going to explain it, I will be explaining it in depth in the magnetic property जब हम ferromagnetic पढ़ेंगे. But just for the sake of completeness I am writing few lines here and few things here. So you keep on writing with me without any question. These are the materials which contain permanent electric dipoles, and all dipoles are aligned parallel to each other, and dipoles are aligned parallel to each other, On the application of electric field, on the application of electric field, these materials get strongly polarized. These materials get strongly polarized and remain polarized even on the removal of field, even on the removal of field, that is, these exhibit spontaneous polarization, These materials exhibit hysteresis curve in their characteristics. These materials exhibit hysteresis curve in their characteristics. These materials remain ferroelectric up to Curie temperature. These materials remain ferroelectric up to Curie temperature. Above Curie temperature, they become paraelectric. Above Curie temperature, they become paraelectric. This is polarization, this is electric field. So you are having this kind of curve, and this curve is known as hysteresis curve. ठीक से नहीं बना, फिर से बनाते हैं. This is polarization, this is electric field. This kind of curve is known as hysteresis curve. This peak value of polarization is known as saturation polarization. The value of polarization in the absence of electric field, this is PR, is known as remanent or residual or spontaneous polarization. It is known as coercive field. EC is coercive field. It is known as coercive field. Some examples of this material are barium titanate, lead titanate, etc. Barium titanate, lead titanate, etc. In fact, all the ferroelectric materials will exhibit piezoelectricity also. Vice versa need not be true. So we can have a note, that is, अगर मैं बीन डायग्राम बनाऊं तो this is piezo, the greater one is, and उसके अंदर the smaller one is ferro. So all ferroelectric materials are piezoelectric. All ferroelectric materials are materials are piezoelectric, piezoelectric, but vice versa may not be true, but vice versa may not be true, may not be true. All ferroelectric materials are piezoelectric, but vice versa may not be true. For example, quartz is piezoelectric but not ferroelectric. Quartz is piezoelectric but not ferroelectric, but not ferroelectric. Quartz is piezoelectric but not ferroelectric. So please note it down quickly. ये जल्दी से लिख लें. Do it quickly. मैंने क्या कहा कि यहां कुछ भी नहीं समझाऊंगा तो आपको क्वेश्चन नहीं पूछना चाहिए था. यू प्लीज ट्राई इट. Do it quickly. So, this was all about the piezoelectric and ferroelectric materials, right. Is it done? So, with this topic we have completed this very lengthy chapter. We have studied conductor, semiconductor and insulator. All these has been covered. Now, this chapter electric properties of material has been covered, and it has been covered beautifully. We are now moving towards the fourth chapter. Up till now we have studied first introduction of the material science, then the chapter 1, that is chemical bonding, atomic structure and chemical bonding, second crystallography, third electric properties of materials. The fourth chapter is magnetic properties of material. Chapter 4 is magnetic properties of materials. When a material is put into the magnetic field, if it is attracted or repelled away from the magnetic field, then we would be saying that the material is magnetized, and such materials are known as magnetic material. But suppose we put a material into magnetic field and it is neither attracted nor repelled away from the magnetic field, then we cannot say it as a magnetic material. Magnetic field lines are represented like this. These are the magnetic flux lines. These are magnetic flux lines. This is denoted as B. Suppose we put a material, this is our material, and this material is put into a magnetic field. This material is put into a magnetic field. ये material magnetic field में put गया and field lines are repelled away. So it is known as magnetic material. Suppose we put this material into a magnetic field or any material into the magnetic field and field lines are attracted like this. So this is the attraction taking place. It is also magnetic material. But if it is non-magnetic material, then no matter what magnetic field you put, nothing is going to happen with the flux lines. Sometimes people get confused if it is a non-magnetic material, field lines will not pass. No, they will pass, but without changing. whereas in the magnetic material they will definitely change. So these two are basically magnetic materials. Attraction or repulsion, any phenomena may take place. This is known as magnetic material. But if nothing happens, ना attraction हो रहा ना repulsion, then the material is known as non-magnetic material. Then material is non-magnetic material, right? So magnetic materials are those materials which are put into magnetic field, then either they are attracted by the field or they are repelled away from the field. Such materials are known as magnetic material. If a material is put into the magnetic field and nothing happens to the field, neither attraction nor repulsion, then such material is known as non-magnetic material. This effect of attraction or repulsion is known as magnetization. So if material is non-magnetic, then its magnetization is 0. But if it is magnetic, then it will exhibit certain value of magnetization. In fact, all materials are magnetic. All materials are magnetic except vacuum. Vacuum is the only true non-magnetic medium. Except vacuum, everything is magnetic. But for scientific use, for application, we consider those materials as magnetic materials where the effect of attraction or repulsion is strong. Those materials which has weak magnetization, we call them as non-magnetic material. Although in the true sense, there is nothing like non-magnetic material except vacuum. Vacuum is the only true non-magnetic material. Everything apart from vacuum is magnetic, right? So let us try to write few lines here about the magnetic materials. Let us try to write. अरे फोटो इलेक्ट्रिक पढ़ लो, बहुत छोटी चीज़ें हैं, उनके लिए कहाँ हमको परेशान करोगे. कुछ नहीं, लाइट पड़ी, फोटो मीन्स फोटान, लाइट की वजह से कोई करंट फ्लो करे तो वो फोटो इलेक्ट्रिक करंट हो गया. लिखें, when a magnetic material is put, when a magnetic material is put into a magnetic field, when a magnetic material is put into a magnetic field, into a magnetic field, when magnetic materials are put into a magnetic field, then either they are attracted by the field, then either they are attracted by the field, either they are attracted by the field, or repelled away from the field, or repelled away from the field, or repelled away from the field. Either they are attracted by the field or repelled away from the field. Full stop. All materials show some magnetic effect. All materials show, SHOW, show some magnetic effect. All materials show some magnetic effect. But in many substances, the effects are so weak, but in many substances the effects are so weak that the materials are often often considered to be non-magnetic, that the materials are often considered to be non-magnetic. However, a vacuum is the only true non-magnetic medium. However, a vacuum is the only true non-magnetic medium. However, a vacuum is the only true non-magnetic medium. There is a difference between electric dipole and magnetic dipole. Electric field is defined as, electric dipole is basically what? This. Basically, electric field is defined as voltage per unit length, volt per meter. So, voltage can exist even in open path, and that's why electric dipole is like this, plus Q and minus Q. So, because the voltage can exist in an open path, so it can be an open structure, two charges separated by each. It is dipole. Electric monopole also exists, plus Q. There are several bodies which have only positive charge, they are known as electric monopole. There are several bodies which have only negative charge, they are known as electric monopole. So, electric monopole also exists in the nature. Magnetic field is defined as current per unit length. Current per unit length. This is defined as magnetic field. Current cannot flow in open path. So, to get magnetism, we cannot have open structure. There must be some closed path. So, the fundamental element for magnetism cannot be open path like this. Here the dipole is like this. A small circular closed current loop is known as dipole. One end of this dipole, from where the current is leaving, that is known as north pole, and where it is entering, that is known as south pole. So, a small circular current loop, that can be considered as a magnetic dipole. Suppose I want to cut it to make the magnetic monopole. It does not exist. Why? As soon as I cut, the current flow will stop. So, we will not get any magnetism. It means magnetic monopole does not exist in reality. Even the smallest magnet will have magnetic dipole. It cannot be magnetic monopole. First thing. Second thing. What is the basic reason behind electric field? Just the presence of charge, that is sufficient to develop the electric field, electric properties. But for magnetism, only presence of charge is not required, current is required. Current is basically motion of charge, and that too in the closed circuit. So, motion of charge in the closed circuit means angular motion of charge is basic reason behind the magnetism. जब तक एंगुलर मोशन ऑफ चार्ज नहीं होगी, तब तक मैग्नेटिज्म पिक्चर में नहीं आएगा. दिस यू मस्ट नो वेरी वेल. सो मैग्नेटिज्म इज बेसिकली ड्यू टू angular motion of charge. Now let us start discussing few fundamental things, and from there we keep on talking several parameters. So we will be talking about magnetic permeability. Magnetic permeability. We'll begin with this. This is magnetic permeability. Suppose we have a material like this, and we are winding wires on this material. The wires are wound like this in the coil form. Basically, we are making a solenoid, right? We are making a solenoid like that. It is going. So here a current is flowing in this material, and let us suppose there are n number of turns. N is number of turns, and I is the current flowing. L is the length of this structure. Let us suppose this is L. L is length. Then because of this current, we will have a magnetic field, and that magnetic field intensity is defined as, we will have a magnetic field, and that magnetic field intensity is defined as, magnetic field intensity, magnetic field intensity is given as H is equal to N I upon L. This is N I upon L. N is just number, so unit of H is ampere per meter. This is ampere per meter. This is the unit of H. Magnetic field intensity is given as Ni upon L. N is just number of turns. So our number of turns is 1, then I by L. Otherwise, if it is 100, then Ni by L. That is the value of magnetic field intensity. We define here magnetic flux density. Flux is just like charge. So here we talk about flux. Flux is per unit area. Basically, that is the 2D quantity, and field is basically 1D quantity. So magnetic flux density is given as, magnetic flux density, magnetic flux density is given as, this is B is equal to mu r mu naught into H, that is mu into H. Here mu is equal to mu r into mu naught. This mu is known as magnetic permeability of material. It is known as magnetic permeability of material, magnetic permeability of material, right? And this mu r is known as mu r, very important, relative magnetic permeability, relative magnetic permeability of material. Mu naught is known as permeability of material, vacuum, magnetic permeability of free space or vacuum. It is magnetic permeability of free space or vacuum. So mu naught is equal to 4 pi into 10 to the power minus 7 Henry per meter. Henry per meter. This is magnetic permeability. Mu r is relative parameter. So mu r can be equal to 1 only for the vacuum, because we are defining with respect to vacuum. So mu r is equal to 1 for vacuum. For any other material apart from vacuum, it cannot be 1, because you are comparing with vacuum. So either it is greater than vacuum or less than vacuum, but can never be equal to vacuum. So mu r does not equal to 1 for other material, other medium या material जो भी कह लें, ठीक. So this is the definition of magnetic permeability. Very important parameter for us. This will relate one dimensional quantity magnetic field with the two dimensional quantity magnetic flux. Please note down. जो B की यूनिट होती है मैग्नेटिक फ्लक्स की यूनिट, वो टेस्ला है. यूनिट ऑफ B, दिस इज टेस्ला, या इसे वेबर पर मीटर स्क्वायर भी कहते हैं. वेबर, WB इज वेबर पर मीटर स्क्वायर. बोथ आर सेम. डन. शैल वी गो अहेड? राइट, आगे चलते हैं. नेक्स्ट, मैग्नेटिक डायपोल मोमेंट. मैग्नेटिक डायपोल मोमेंट. A small circular current carrying loop is known as magnetic dipole. A small circular current, a small circular current carrying loop is known as magnetic dipole. A small circular current carrying loop is known as magnetic dipole. This is a current loop. This is a current loop. X, Y, Z. ठीक. Suppose this loop is carrying current I and the radius of the loop is R, right? So the magnetic dipole moment is, let us suppose it is kept in XY plane. So magnetic dipole moment is defined as magnetic dipole moment is defined as Pm is current flowing through it into area into unit vector n cap, which will give the direction of dipole moment. Actually, direction is calculated like this: right hand screw rule. You curl the fingers of right hand along the direction of current flow, then thumb will show the direction of dipole moment. So if it is in the xy plane, thumb is going along positive z axis out of the plane. If current direction is changed, then thumb would be going towards the plane, inside the plane. So if thumb is going towards the plane, inside the plane, then it is known as minus az axis. So for clockwise, it is minus z cap, and for the anti-clockwise, like this current is flowing, then it is along the z direction. So we can have current I multiplied by pi r square into z cap. Z cap is unit vector along z axis. This is the magnetic dipole moment. This is the value of magnetic dipole moment. इसकी यूनिट अगर हम बात करें, so this unit is current की यूनिट एम्पियर and इसकी यूनिट मीटर स्क्वायर, एम्पियर मीटर स्क्वायर. The second unit is Bohr magnetron. Bohr magnetron. One Bohr magnetron is given as one Bohr magnetron. This is given as 9.27 into 10 to the power minus 24 ampere meter square. This is one Bohr magnetron. This is one Bohr magnetron. But it is magnetization of a particular dipole. We cannot apply magnetic field on a particular dipole. We would be applying magnetic field on a material. So practically, to define the magnetization, we have to define for a volume. So like we did for the polarization, similarly we would be doing here for magnetization. There I said that polarization is dipole moment per unit volume. Here also I would be saying that magnetic dipole moment per unit volume would be known as magnetization. But before that, you please note down this. Quickly do it. बेटा जो मटीरियल साइंस पढ़ रहे हो, महतोन्स, आई एम रीडिंग योर मैसेज. वॉट एवर इज इन द सिलेबस, फर्स्ट रीड इट. दिस इज नॉट द टाइम टू टेक लॉट्स ऑफ नॉलेज. फर्स्ट यू क्रैक द एग्जाम, देन मिलिए मुझसे, चाय पे चर्चा करेंगे. बहुत सारे इलेक्ट्रिसिटी कैसे क्या हो रही, वो सब बातें करेंगे. यहाँ अगर एक एक क्वेरी लेते रहेंगे ना, तो इस क्लास में मोर देन 1000 स्टूडेंट्स आर लाइव. ठीक. सो इट वुड बी वेरी डिफिकल्ट फॉर मी टू टेक. बहुत सारे मेरे पास ऑफ ट्रैक क्वेश्चन आते रहते हैं, जैसे आपने पूछा वैसे सभी लोग कमेंट बॉक्स में पूछते रहते हैं. मैं सिर्फ उन्हीं क्वेश्चंस को ले रहा हूं जो पर्टिनेंट हैं, जो सब्जेक्ट से जुड़े हुए हैं. आई नेक्स्ट वी आर गोइंग फॉर द मैग्नेटाइजेशन. It is defined as magnetic dipole moment per unit volume. It is defined as magnetic dipole moment per unit volume. It is defined as magnetic dipole moment per unit volume. defined as magnetic dipole moment per unit volume. Suppose n is number of magnetic dipoles, number of magnetic dipoles per unit volume, and Pm is magnetic dipole moment of each dipole, magnetic dipole moment of each dipole. Then what would be the magnetization? Pm, Pm, Pm up to n times. So it is equal to m is equal to n into Pm. It is equal to n into Pm. Unit of m is 1 by meter cube, and Pm has unit ampere into meter square. So it will become ampere per meter. It is ampere per meter. Very interesting. Ampere per meter is nothing but the unit of magnetic field. It means magnetization is nothing but an induced magnetic field inside the material. So let us suppose this is a magnetic material, and when you apply external magnetic field, you apply, let us suppose you put this material into certain magnetic field, you apply certain magnetic field H. So this material will induce some magnetization M also. So overall flux is due to both M and H. M is internally induced magnetization and H is applied field. So you can write total magnetic flux density, magnetic flux density in a magnetic material, in a magnetic material is due to total magnetic flux density in a magnetic material is due to first applied magnetic field, and second magnetization. Second is magnetization. So mathematically B is equal to total field H plus M, and this multiplied by mu naught. This is equation 1. This is equation 1. H is applied field, M is induced. So H plus M vector sum, total field, mu naught से multiply कर दो, you will be getting total flux. Suppose you have mu r known, then this value I say to calculate in the last reading, B is equal to mu r mu naught into H. Both of these relations are giving same thing. So from equations 1 and 2, mu naught H plus M is equal to mu r mu naught into H. Mu naught will get cancel out. So from this it comes out as M is equal to mu r minus 1 into H. Very important relationship. Is that if mu r is equal to 1, then 1 minus 1 0. No matter whatever field you are applying, magnetization is 0. And that's why I said that vacuum is purely non-magnetic, because mu r is equal to 1 for vacuum. But apart from vacuum, for any other material, mu r cannot be equal to 1. And if it is not equal to 1, then this mu r minus 1 is non-zero value. And if this mu r minus 1 is non-zero value, if you applied any field, then the product of these two will remain non-zero. It means there would be certain magnetization. So everything apart from vacuum is showing certain magnetic behavior, that is having certain magnetic character, non-zero value of magnetization. But we would be saying it as a magnetic material for our practical purposes when the value of m is large. When m is small, we can neglect it and we can assume the material as non-magnetic. One more thing, if mu r is greater than 1, then mu r minus 1 is positive, and if mu r minus 1 is positive, then m and h are in the same direction. It means material is magnetized along the direction of field. So along the direction of field means material is being attracted. So if mu r is greater than 1, then magnetization is along the direction of field. It means material is being attracted towards the field. But suppose mu r is less than 1, so mu r minus 1 will be negative, and if it is negative, it means m and h are opposite to each other. So if m and h are opposite to each other, means if field is going this direction, magnetization is this direction. So material is magnetized opposite to the field, means it is repelled away. So whether attraction will take place or repulsion will take place, it will depend upon the value of mu r, whether it is greater than 1 or it is less than 1. This mu r minus 1 can be known as a new value. We can replace it by susceptibility. So m is equal to chi m into h. Chi m is very important parameter because magnetization is directly proportional to this chi m, where chi m is nothing but mu r minus 1. Basically susceptibility is nothing but permeability minus 1. This is known as magnetic susceptibility of material. Magnetic susceptibility of material. Susceptibility of material. Chi m may be positive or negative depending upon magnitude of mu r. If mu r is greater than 1, then chi m is positive. If chi m is positive, m and h are of same sign, so material is attracted towards the magnetic field, attracted towards the magnetic field. Yeah, magnetic field is attracting to the material, both are same, towards the magnetic field. Material is attracted towards the magnetic field, towards the magnetic field. And if it is negative, then material is repelled away from the magnetic field. Material is repelled away from the magnetic field, repelled away from the magnetic field, from the magnetic field. Material is repelled away from the magnetic field, right? So this is all about the material magnetization. Please note down. Here we started. Yes, Akhilesh, you are right. Magnetization is basically whether it is attracted or repelled away. That is known as magnetization. You put the material into a magnetic field, and in the presence of magnetic field, whether the material is attracted or repelled away, that is known as magnetization. Yes, Milu, what you have written, that is derived. So you can see your answer is correct. Yes, magnetization and polarization are analogous to each other. Only difference is there we talk about the behavior of material under the influence of electric field. Now here we are talking the behavior of material under the influence of magnetic field, nothing else. Then the whole topic will run hand in hand as we did in the polarization case. It would be similar to the polarization. Mukul, we can't say that equal contribution. We are not saying equal. It will depend upon the magnitude, whether H magnitude is higher or B magnitude is higher. We are taking just the vector sum. Whatever is the magnitude, accordingly it will get added. Achilles, keep patience, you will get answer for your question very soon. Do it quickly. Shall we go ahead? Waiting for your response. Good. Origin of origin of permanent magnetic dipole moment. I told you कि angular motion of charge is responsible for magnetism. Whenever there is angular motion of charge, then it will create a magnetic dipole moment. So you see, at the atomic level, there is an atom in which electrons are revolving like this. This is electron. So this electron has charge, and this charge is in angular motion. So this orbital angular motion of electron will contribute to a magnetic dipole moment. So the first factor towards the magnetic dipole moment of an atom is angular orbital motion of the electron. But it is not the only thing. We have to observe few more things. Electron move like this as well as it spins at this position. This spin. So this spin motion of electron is also an angular motion of charge. So this spin motion is also contributing to the magnetic dipole moment. So there are two factors due to electron, one orbital angular momentum and another spin angular momentum of electron. The third one is this nucleus also spins at its position. So this nuclear spin is also contributing to the magnetic dipole moment. So in general, at the atomic level, for a particular atom, there are three factors contributing to the magnetic dipole moment. First, electron orbital angular motion. Second, electron spin angular motion. And third, nuclear spin angular motion. बट एक चीज देखिए, न्यूक्लियस में जितने पॉजिटिव चार्ज होते हैं, सारे ऑर्बिट्स को मिला करके उतने ही नेगेटिव चार्ज होते हैं. सो ऑर्बिटल एंगुलर मोशन ऑफ इलेक्ट्रॉन्स एंड न्यूक्लियर मोशन ऑफ न्यूक्लियस, these will try to cancel the effect of each other. So their contribution in magnetic property will be very small. They will try to balance each other, although they cannot 100% balance each other, but they will try to balance each other. So their contribution would be very small, very negligible. So a strong magnetic behavior would be observed due to the third factor. Third factor is electron spin dipole moment. So if you have non-zero spin dipole moment, then you have a strong permanent dipole associated with each atom. And if you have non-zero spin dipole moment, it means you have absence of permanent dipole. Although permanent dipole is because of three factors, like remaining two factors are very weaker, they can be neglected, but this spin dipole moment cannot be neglected. So we can write angular motion of charge, angular motion of charge is responsible for creation of a magnetic dipole, for a creation of a magnetic dipole. Angular motion of a charge is responsible for creation of a magnetic dipole. At the atomic level, in general, there are three factors contributing to the at the atomic level. In general, there are three factors contributing to the total magnetic dipole moment, to the permanent dipole moment of an atom, to the permanent dipole moment of an atom. Permanent dipole moment of an atom. At the atomic level in general, there are three factors contributing to the permanent dipole moment of an atom. Magnetic dipole moment basically. First, इस चैप्टर में डायपोल का मतलब बाय डिफॉल्ट मैग्नेटिक डायपोल. फर्स्ट, इलेक्ट्रॉन ऑर्बिटल एंगुलर मोमेंटम. इलेक्ट्रॉन ऑर्बिटल एंगुलर मोमेंटम. एंगुलर मोमेंटम. सेकंड, इलेक्ट्रॉन स्पिन एंगुलर मोमेंटम. इलेक्ट्रॉन स्पिन एंगुलर momentum. Third, nuclear spin angular momentum. Nuclear spin angular momentum. Nuclear spin angular momentum. Magnetic properties of materials. Magnetic properties of materials. Magnetic properties of materials. Of materials are mainly influenced by. Are mainly influenced by. Influenced by. Properties of materials are mainly influenced by electron spin angular momentum. Electron spin angular momentum. Remaining two we can neglect, although they are also contributing. If in general they ask all the components, then you have to consider all three. Otherwise, remaining two can be neglected and electron spin can be considered. देखो बेटा, ऐसी कोई भी फरमाइश आप ना करें जो मैं पूरा नहीं कर पाऊंगा. डू यू फील इज इट प्रैक्टिकली पॉसिबल ऋत्विक? इज इट पॉसिबल? कैसे आप लोग कर दे? आराम से वीडियो अपलोड होगा, एक एक उठा करके देखिएगा वहां से. Note down, these are the regions responsible for the permanent magnet. Akhilesh, answer for your question you may have got. Done? So now we would be concentrating ourselves up to the discussion of this one. This is electron spin angular momentum. So this will contribute a dipole. That dipole is known as permanent dipole, right? So electron, although permanent dipole is because of three reasons, but we are neglecting other two. We are saying mainly because of this. So let us put a heading: electron spin dipole moment. Electron spin dipole moment. Electron spin dipole moment. Electrons can have either anti-clockwise spin or clockwise spin. So let us suppose any state is fully filled. So you have anti-clockwise and clockwise both. So if the dipole moment due to anti-clockwise is in this direction, then because of clockwise it is opposite. So both of them will cancel each other. Both of them will cancel each other. So net dipole moment is, suppose what I am saying that if any state is paired, so it means it has two electrons, one will contribute dipole outside, then one inside, they will cancel each other, and net dipole moment would be 0. So elements which have completely paired electrons, they have 0 net spin dipole moment, and we will be saying that they do not carry any permanent dipole. Although they have permanent dipole because of those two factors, but they are negligible, so neglected. So we will say that we do not have any permanent magnetic dipole. But if any element is having a single electron, unpaired electron, either anti-clockwise or clockwise kuch bhi, so this will contribute a non-zero magnetic dipole moment. So unpaired electrons are contributing to the permanent magnetic dipole moment of an atom. So they are going to decide the magnetic character. You see, transition elements like ferrous, nickel, cobalt, all these are very strong magnetic materials. So when you see their atomic structure, you will find out that they have unpaired electron, and particularly these unpaired electrons are found in 3d orbital, because in these elements you will find out that 1s, 2s, 3s, 3p, then 4s is first filled and then 3d is filled. So 4s becomes paired most of the cases, barring few exceptions, but 3d remains unpaired. So how many electrons are unpaired in the 3d, that is going to decide the presence of permanent dipoles in these materials. So let us write this: elements having completely paired electrons, possess 0 net electron spin dipole moment. 0 net electron spin dipole moment. 0 net electron spin dipole moment. Elements having completely paired electrons possess 0 net electron spin dipole moment. ठीक? Elements having unpaired electrons, elements having unpaired electrons possess non-zero electron spin dipole moment. Elements having unpaired electrons possess non-zero electron spin dipole moment. Non-zero electron spin dipole moment. Transition elements such as ferrous, nickel, cobalt, etc. possess permanent magnetic dipole moments, permanent magnetic dipole moments due to unpaired electrons in inner 3D orbit of element, in inner 3D orbit of element, in inner 3D orbit of element, right? Transition elements such as ferrous, nickel, cobalt, etc. possess permanent magnetic dipole moments due to unpaired electrons in inner 3D orbit of the elements. If Z is number of unpaired electrons in inner 3D orbit of element, Pb is one Bohr magnetron, that is 1 Pb is 9.27 into 10 to the power minus 24 ampere meter square. Then magnetic dipole moment is Pm is Z into Pb. This is Pm. Pm is Z into Pb, right? Now you see Pm is Z into Pb. Example के तौर पर, let us suppose I talk about iron. Iron has atomic number 26. So its configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d नहीं, पहले 4s2 भरता है and then 3d6 like this. So how many unpaired electrons are there? D has 5 energy states, I told you in first chapter. So first unpaired electrons, single electrons, 1, 2, 3, 4, 5, and then pairing will start. So there are 6 electrons they have filled. How many unpaired electrons are there? Z is equal to 4 unpaired electrons. So you have 4 unpaired electrons, and if there are 4 unpaired electrons, then permanent magnetic dipole moment Pm is equal to 4 Bohr magnetron. Sometimes they ask a question कि one electron will have how much magnetic dipole moment, so it is equal to 1 Bohr magnetron. So if there are 4 electrons unpaired, so they will have 4 Bohr magnetron. Pb is Bohr magnetron. Some of the books represent Pb by mu b also, so you may get like this, both are same, mu b or Pb, they represent 1 Bohr magnetron. Here onwards, if I say that the material is having permanent magnetic dipole moment, it means by default it has electron spin dipole moment. And if I say that material does not have permanent magnetic dipole moment, it means there are paired electrons and material does not have any permanent dipole moment. Nuclear spin will try to balance not electron spin, instead the orbital angular motion, because orbits में जितने इलेक्ट्रॉन हैं न्यूक्लियस में उतने ही प्रोटॉन होंगे. So orbital motion of electron will try to balance the nuclear motion. I said that, Karthik, there are 3 factors which are responsible for the total magnetic behavior. These 3 are responsible. but remaining two we are neglecting. We are mainly concerned with magnetic properties of materials are mainly influenced by electron spin angular momentum. साफ साफ लिखा हुआ है. आप लोग शायद सो रहे हैं. If you are sleeping, then wake up. Is it done? Shall we go ahead? Yes, class timing will remain 8:30 onwards. Have you noted it? Right. So here onwards, if I say that if a material is having permanent magnetic dipole, it means material is having a non-zero value of these spin dipole moments. It means it is having unpaired electrons. And if I say that material does not have permanent dipole, it means material is having paired electrons. Now, classification of magnetic materials. Classification of magnetic materials. Magnetic materials are broadly classified in 5 categories. The first one is diamagnetic material. Diamagnetic material. The second one is paramagnetic material. Paramagnetic material. Third one is ferromagnetic material. Ferromagnetic material. Fourth is antiferromagnetic material. Antiferromagnetic material. And the fifth is ferrimagnetic material. Ferrimagnetic material. Out of these, mu r for diamagnetic material is less than 1. So susceptibility is negative. For remaining 4, susceptibility is पॉजिटिव. बाकी 4 के लिए ससेप्टिबिलिटी पॉजिटिव है because mu r is greater than 1. So let us try to discuss one by one all these materials. Please write the name of all these, then we would be discussing each one. चलिए जी आगे चलते हैं, लेट्स गो फॉरवर्ड. So first material which we are wanting to study is diamagnetic material. Actually diamagnetic materials are those materials in which electrons are paired. Electrons are paired like hydrogen. If you recall in hydrogen H and H, basically H2 molecule. H तो exist ही नहीं करता, it exists in the form of H2 molecule. So in H2 molecule I told you कि the structure is something like this. The structure is something like this if you recall. And both of the electrons are here. So it is paired, and if it is paired, net spin dipole moment would be 0. So this material is diamagnetic material. So these are the materials which have no permanent dipoles. Permanent dipole I mean spin dipole. So these are the materials which does not contain permanent magnetic dipole moments. So these materials do not contain permanent magnetic dipole moments. These materials do not contain permanent magnetic dipole moments. So their magnetic behavior is very negligible. So their value of mu r is very small, that is less than 1, and that is the reason why susceptibility is very small. These materials exhibit magnetism because of the remaining two factors, orbital electron angular momentum and nuclear spin. ये दोनों जितना कैंसिल नहीं कर पाएंगे, सो जो उसका रिजल्ट होगा दैट विल गिव देम मैग्नेटिज्म. सो दे आर वीकली मैग्नेटाइज्ड and hence susceptibility is very small and negative value. So these materials have a small and negative value of magnetic susceptibility. These materials have a small and negative value of magnetic susceptibility. Small and negative value of magnetic susceptibility. These materials, one moment, let us suppose there is a material which is having permanent dipoles. So that material will exhibit certain magnetic behavior. Now if you increase the temperature, then orientation of dipoles will change and magnetic behavior will change. So the materials which are having permanent dipoles, their magnetic susceptibility will be affected by the temperature. But in this material there is no permanent dipole. So by increasing temperature, what you can disturb? जो चीज है ही नहीं उसको temperature लगा के कहाँ से disturb कर लोगे? So magnetic susceptibility of diamagnetic materials is independent of temperature. Magnetic susceptibility of diamagnetic materials is independent of temperature. Magnetic susceptibility of diamagnetic materials is independent of temperature. These materials are repelled away from magnetic field because their susceptibility is negative. So negative means repulsion will take place. So these materials repel, या तो ये खुद रिपेल कर रहे हैं या रिपेल हो रहे हैं, बात एक ही है. सो दीज मटीरियल्स रिपेल magnetic flux. These materials repel magnetic flux. So let us suppose you have a diamagnetic material. This is your diamagnetic material, I am assuming it is ideal diamagnetic material. So if you apply a magnetic field, it will repel. All the magnetic flux would be repelled if it is ideal one. If it is practical, very small may go, that is negligible. So in an ideal diamagnetic material, magnetic flux inside the material should be 0. So in a diamagnetic material, B is equal to 0. अंदर कोई भी फ्लक्स नहीं है, सब इसने रिपेल कर दिया है. But B is equal to mu naught H plus M. So we are having mu naught H plus M, that is equal to 0. Mu naught cannot be 0. Mu naught is universal constant. The value of mu naught is always 4 pi into 10 raised power minus 7 Henry per meter. You do not need to remember it if you are not from EC electrical, just to know this value. So it is a constant, so it cannot be equal to 0. So what can be 0? H plus M is equal to 0. It means what? M is equal to minus H. If M is equal to minus H, you can say that M by H is equal to minus 1. M by H is chi M is minus 1. So magnetic susceptibility for a perfect diamagnetic material is minus 1. But magnetic susceptibility is mu r minus 1, that is mu r is equal to 0. So condition for perfect diamagnetism is magnetic permeability should be equal to 0. Condition for perfect diamagnetism, ideal diamagnetism, perfect diamagnetism. This is the condition for perfect diamagnetism. Perfect diamagnetism. Some popular diamagnetic materials, I am giving you some example. So example is bismuth, copper, diamond, gold, lead, mercury, water, etc. हाइड्रोजन पहले ही बता दिया. So this is all about the diamagnetic material which you should know. हमने आपको लिखा दिया. Please do it quickly. यहाँ से शुरू किया था. हाँ, diamagnetic. Do it. Magnetic susceptibility is defined as ability of material to be magnetized under the influence of unit applied magnetic field. This is nothing but mu r minus 1. It can be defined as magnetic susceptibility can be defined as ability of material to be magnetized for unit applied magnetic field. Done? Let's go ahead. Do it quickly. Shall we go ahead? Next, paramagnetic materials. Briefly, we would be talking about all the materials. So, paramagnetic materials. These are the materials which contain permanent magnetic dipoles, but the dipoles are randomly oriented. They are equal in magnitude and they are randomly oriented. Because of random orientation, they will cancel each other. So, in the absence of magnetic field, you will not get any magnetization. The magnetization which we get absence of electric field, that is known as spontaneous magnetization. So, these materials will have zero spontaneous magnetization. Although they are having large number of permanent dipoles, these dipoles are equal in magnitude, but they are randomly oriented. Because of random orientation, they will cancel each other. So, net magnetization in the absence of field is 0. Now, let us suppose we apply a magnetic field. So, when we apply a magnetic field will apply torque on these dipoles. So, because of that torque, they will get rotated parallel to the field. So, when they get rotated towards the field, you will get certain magnetization. So, M is directly proportional to H. You keep on increasing the H, the dipoles will keep on rotating towards the magnetic field, and this way the magnetization will keep on increasing. But suppose you are increasing the temperature. So, if you are increasing the temperature increases thermal energy, which brings entropy. Entropy is degree of randomness. So, temperature increase will try to randomize these dipoles, and if there is a randomization, then net value would become less, average value would be less. So, magnetization will decrease. So, M is inversely proportional to temperature. If I connect these 2 points, then I can say that in these materials, M is directly proportional to H by T. So, this M directly proportional to H by T, we can bring a proportionality constant C H by T. We can write it as M by H is equal to C by T. We know that M is equal to chi M into H. It means what? M by H is chi M, alright. So, this is written chi M. So, chi M is equal to C by T. This is known as Curie law. This equation is known as Curie law. This equation is known as Curie law. Is known as Curie law. As Curie law. And this proportionality constant C is known as Curie constant. It is known as Curie constant. This law actually relates the relationship of susceptibility versus temperature for a paramagnetic material. For a paramagnetic material, if temperature is increasing, the susceptibility is decreasing, and the relationship is something like this. So, this is implication of this Curie law. So, we can say that paramagnetic materials are those materials which contain permanent magnetic dipoles, and these permanent magnetic dipoles are randomly oriented. So, you can write like this. Let us write these materials contain permanent magnetic dipoles, permanent magnetic dipoles, magnetic dipoles, which are randomly oriented, which are randomly oriented, which are randomly oriented. Hence, net magnetization, hence net magnetization in the absence of field, absence of field is 0. Net magnetization in the absence of field is 0. On the application of field, on the application of field, application of field, we get a small value of magnetization, a small value of magnetization along the direction of field, along the direction of field. So these materials have, so these materials have a small and positive value of magnetic susceptibility, small and positive value of magnetic susceptibility, small and positive value of chi m, magnetic susceptibility. Some examples of paramagnetic materials are, some popular examples of paramagnetic material are aluminum, aluminum, calcium, lithium, oxygen, इत्यादि, etc. So please note it down, कृपया से लिख लें. This is all about the paramagnetic material which you should know. Sir, is human body also possesses magnetic property? Yes, it possesses magnetic property, and I don't have information because it is not a single element which is making us. So we cannot say it is di, para, what kind of behavior it shows, but it definitely shows magnetic behavior. It is a magnetic body, and that's why when you come into contact with this high tension wire 11,000 kV etc. So there is a strong magnetic field and that immediately attracts your body. So since your body is being attracted, it means it cannot be diamagnetic, it is either para, ferro, anti-ferro, whatever it may be, but cannot be diamagnetic. So you will be attracted, and then strong magnetic energy would be imparted by the field in your body. Your body will not be able to withstand that much magnetic energy, and it will immediately burn and the system will collapse, breakdown will take place. Is it done? Yes, not wonderful, but we will have a last experience which we cannot tell to anybody. Here I would like to give one note. Some paramagnetic materials do not obey Curie law. Instead, they obey Curie's law. ठीक. Some paramagnetic materials do not obey Curie law, instead they obey Curie's law. So chi m is equal to C upon T minus theta. This law is known as Curie's law. Curie's law. Here C is known as Curie constant and theta is known as Curie temperature. इस टेम्परेचर को हम लोग Curie temperature कहते हैं. T तो टेम्परेचर है ही. So if you plot this, susceptibility would be looking like this. Chi m versus temperature. We will have a temperature like this. This is your theta. So above theta material will follow Curie's law. It is like this. And in this range it is known as paramagnetic material. It is paramagnetic material. Paramagnetic material. But below this temperature it does not obey Curie law. Sorry, it is something like this. Obeys mirror image of this. Below this temperature the material does not remain paramagnetic. Instead it is ferromagnetic. It is ferromagnetic. So in other words, we can say that in ferromagnetic materials with increase in temperature, magnetic susceptibility increases, whereas in paramagnetic materials with increase in temperature, magnetic susceptibility decreases. That is the implication of this graph. What is ferromagnetic material? That we would be discussing in next class. आज के लिए बस इतना ही है. In the next class, we will be discussing about ferromagnetic materials, anti-ferromagnetic materials, ferrimagnetic materials, and then this chapter would be over. Then we would be talking about the mechanical properties of materials. So that is a small chapter. Few fundamental properties we need to discuss about the mechanical properties, and then we would be moving towards the next chapters. Thank you. आज के लिए बस इतना. अखिलेश, मैंने कहा कि यदि हम टेम्परेचर बढ़ाएंगे तो टेम्परेचर ब्रिंग्स रैंडमनेस, सो दैट टेम्परेचर विल ट्राई टू मेक डायपोल्स रैंडम. बेसिकली वाइब्रेशन होता है एंड वाइब्रेशन इज नथिंग बट रैंडमनेस. सो इफ डायपोल्स आर गोइंग टू बी रैंडम, then their average value will be very less because they will try to cancel each other, and when in a volume you calculate average value, so that average value would be less. So it means with increase in temperature, because of the randomness, magnetization will decrease. If magnetization is decreasing, susceptibility will decrease. Thank you. कल मिलते हैं. Inverse relationship with the temperature I explained. I am saying that if temperature is increasing, then if temperature is increasing, then randomness in dipoles will increase because atomic vibration happens. And if dipoles are becoming random, let us suppose two dipoles were parallel and they become random, so they will cancel each other, and if they will cancel each other, net magnetization will decrease. So this way magnetization decreases with increase in temperature. Very simple, right? Thank you. We'll be meeting you tomorrow at 8:30. So tomorrow class timing is same. Tomorrow 8:30 AM to 12 noon. This is the class timing. we would be meeting at 8:30. We'll be completing this chapter because this chapter is very small chapter. So it will be completed tomorrow. Next chapter will also be started. Thank you very much.